Good morning to all of you. This is Mark Richardson speaking from Centennial, Colorado, a little bit south of Denver, and welcome to our monthly webinar. I believe the title of this is Curve Fitting 101. We sent this out in our newsletter this month, and we've done this before, but it seems to be a popular subject for those of you who either own MEscope or want to learn a little bit about this step in the process of recovering or extracting modal data, frequency, damping, and mode shapes from experimental data. So that's really what MEscope was originally designed for. There's lots of other functions and features in MEscope, but we're going to focus just on curve fitting here. You can see an animated picture of something very common. You all have it if you own MEscope. It's called the Jim beam. This is just this is the photo model of 3 plates that are held together with 6 cap screws. Very simple, but you can see that even when you put 3 plates like this together, the resonant vibration, the modes of vibration of the structure take on maybe a little more complex motion than you would expect. Modes of vibration are a manifestation of energy that's trapped within the boundaries of the structure. In this case, the aluminum plates. There's a discontinuity between the material, the aluminum material properties and the surrounding air. So when a structure like this is excited by forces, in this case it was impacted with an instrumented hammer. And so the vibration was measured in the form of a set of frequency response functions. That's these measurements over here on the right, and if I use the scroll bar to scroll through, you can see we're looking at the log magnitude of these measurements. So they're complex valued. They have magnitude and phase, or real and imaginary parts, and we're going to look at some of that. So this is standard stuff that comes out of an FFT analyzer, or simply taking some time records from accelerometers and post-processing the data to obtain a set of measurements like this. So this is the most common set of measurements. We're going to go look at some OMA data later on here in the presentation, if we get to it today, where we have not FRFs, but we have cross spectra, or a cross spectrum measurement between each of the accelerometer locations and a reference. But let's dig into this one first and see how we do curve fitting to extract modal parameters from measurements that were made on a structure like this. Now, if I put the point labels on, you can see those are the positions on the Jim beam where accelerometer was mounted, an accelerometer, in this case a triaxial accelerometer. And that's how we're able to get this 3D motion in X, Y, and Z at each point on the model here. And you can see point 15 was where the Jim beam was impacted. Out here, let me just stop the animation here for a second, and we'll just talk about how the data was acquired. It was impacted. The beam was at point 15 in the Z direction. How do I know that? Well, over here on my measurements, we label them with what we call degrees of freedom, or DOFs. So let me expand this out here so you can see a little more clearly. The DOFs, we'll zoom in a little bit, you can see the DOFs of these measurements. As I scroll up to the top, let's go all the way to the top here, you can see The measurements have this M-pound 1, 2, 3, 4 in front of them. This is how I select them and so forth. But the DOFs are what's called a roving DOF, the first DOF in the list, then a colon, then the reference DOF. So 15Z, Z being the vertical direction, at point 15 out here is how this data was acquired. Impacted at 15 in the Z, the accelerometer was placed at point 1 in the and it collected. So over here in the corner, we started with the accelerometer at point 1, and it measured the vibration in the X, Y, and Z. Then we moved the accelerometer to point 2 along the edge of the top plate here, and impacted again at 15Z, and so on, point 3 all the way up to there are 33 points on this structure, and so we collected data at 33 points with a triaxial accelerometer, and that would give us 99 total measurements or FRFs for this structure. So that's quite a bit of data. Personally, I don't like to take this much data. This was done in order to get some nice looking mode shapes, but really 10 good measurements with a triaxial accelerometer like this would be enough to distinguish the different mode shapes. So we call that spatial aliasing as opposed to temporal or the common type of aliasing of a signal when we sample it as a time record. But if we sampled this structure with 10 test points, that would be enough to distinguish the mode shape. So we've actually got more data here than we need in order to obtain or extract the experimental mode shape data, the frequency damping, the mode shape, and then enough points on the model to distinguish one mode shape from another. Now I'm going to start out here with what we call an ODS animation. So MEscope in its simplest form is for looking at or animating ODSs, or operating deflection shapes. Now in this case, it's not a machine operating, it's the deflection of the structure due to impacting it with a hammer. But we use the same terminology. As I move the cursor around, you can see that the picture changes. So it's showing me the data on the model for all 99 measurements as I move the cursor, and the cursor, of course, is at a different frequency. Here it is down at 44 hertz. Now, what is that? Well, that's an ODS, and it looks a little strange. However, when I go down here to these low frequencies, what I expect to see in any set of data that I take is what we call the rigid body motion. This structure was simply impacted while it was setting on some foam rubber and on a tabletop, and so we would expect at the lowest frequencies to see something like this. Now, if I had a bad measurement, I either didn't impact correctly, or the accelerometer wasn't affixed to the structure correctly, I'd see that in this picture. This is showing me all 99 measurements together. So that's the first thing you want to do before doing any curve fitting, is make sure you have a good set of data. And that is what you will see down at the very low frequencies. Now, an even more accurate ODS would be to display just the imaginary part. So I'm going to click over here in my window, and now I have a command up here that says imaginary. So I'm going to just display the imaginary part of the data. And again, I see down here close to the lowest frequency, I'm down here I see a little peak in the data there at 72 hertz. And that's what I'd call a rigid body mode. The structure is just rocking back and forth on the foam rubber that it's sitting on. And there's a little bit of flexure there, but what I'm looking for more so is an indication that I have a good set of data to work with here. So you can see that as I move this cursor just a little bit down here, let me put it right down here. You can see some peaks. There's a little bit of a bending mode of the back plate. That's what I would expect to see in any set of data. We call that first bending. A little bit of flexure of the vertical plate. What else would we look for in a set of data? Well, what we call first torsion, or the first twisting mode. Well, if I go down lower, I'm still seeing just a kind of a bending and more of a rigid body motion there. This is just rocking on the foam rubber base again. Very little flexure, although you can see some torsion in the vertical plate. Let me go down even further. Now it becomes kind of a scatter diagram. And that is expected because at 12 hertz, this is the frequency that we're looking at here, the ODS at 12 hertz, the accelerometer is not measuring the acceleration of the surface very well. And there I hit a limit. It said, do you want to stop animation? Because I went all the way to 0, and 0 is not, there's no data there, so it can't animate it. Let me start the animation going again. And so there we are. Now let's move over to this peak here. Here's a peak in the data, and there I see an ODS that's being dominated by a torsional mode, what I'd call first torsion, the first twist of the back plate or the vertical plate. And that's what we expect to see in any set of data. I don't care whether it's a car body, an airplane wing, a machine tool, a motor and pump, whatever it is. You want to verify that you've got these simple waveforms that are due to the resonant vibration. As I move the cursor along here, you can see there is kind of a bending mode of both top and bottom plates. Now, a better way to look at this data, instead of just looking at one measurement at a time, is to overlay it. So I'm going to click and go to my format menu and select overlay. Now I can see all 99 measurements overlaid, and these peaks show up a little bit better. So this is a good way to look at your data. Now this is acceleration data. How do I know that? Well, I go over here into the properties spreadsheet, and I can see that the units of these measurements are G's per pound of force. So I haven't done any integration to velocity or displacement. Or if I used a laser vibrometer or a prox probe in the case of a machine, then my units would be in different units other than acceleration. But for modal testing, the common sensor is an accelerometer. As I move up here to these higher peaks, now I'm starting to see torsion of the top and bottom plates. That's what I expect to see. And some more bending. Here's what I call first bending, but it's now the plates, all three plates are bending together, sort of out of phase between the top and bottom. Anyway, I know I got a good set of data here. Now we can go into curve fitting. So how do we do that? Well, I'm going to stop the animation. I'm going to go over here to the, I'm right-clicking, and I get what's called a context or a floating menu here. Now the floating menu doesn't have all the commands for the data block window, or in a case of the structure window, if I go over here and right-click, I've only got some of the most commonly used ones. If I want to find all the commands for this window, then I need to go up here to the menu bar, and that's where all the commands are listed, and I can go looking for the command that I want to use. So these are the most common ones, and I'm going to go back over here to the data block window and open, and I executed this one called curve fitting. Now you can see that it's showing me that it's enabled, so If I execute it again, I go back out of curve fitting and I'm just back in the data block display with the properties in the spreadsheet and the graphics over here. Let's go back and turn off the overlay. We'll go back to a row column format, and I'm going to click up here and we'll go to magnitude. This is a common way to look at our data, the magnitude, because it's kind of like looking at it with a magnifying glass. I've got 4 decades of data here. You can see that it's down off of the screen. How did it get there? Well, there's scaling going on, and so all of my magnitudes are pushed to the bottom here, the magnitude format. So I'm going to use this command called maximize, and that will show me again my data with 4 decades of magnification. So I can really look down at the values that are off of the peaks. Now, curve fitting is all about finding the properties of these peaks in the data. The frequency of the peak is a very close approximation of the resonant frequency. The width of the peak is a measure of the damping of the resonance. Now remember, each of these peaks is really an ODS, but with a lightly damped structure like the Jim beam, we say that the ODS peak is being dominated by a resonance. So the whole idea here of curve fitting is to go in and extract the properties of the resonance from this ODS data, from this experimental data. I'm zooming in here a little bit, so let me zoom back out and we'll look at everything. Now, there we go. I got off the screen again. As I zoom, sometimes it will rescale things. So I want to use this command here called maximize, and so I can look at all the data. That's not off the display. All right, let's go back into curve fitting. So I'm going to execute curve fitting. Now what happened here is I still got data, and I'm in a data block. I've got another window down here, or another panel or graphics area, and it's called the mode indicator. So from any one measurement, I can see some peaks in there, but depending on where that measurement was taken on the structure, I may not see all the resonance peaks. And that's because when I get close to a node line or a point where the mode shape is 0, point in direction, then the peak's not going to show up. There's not going to be any evidence of the resonance in that measurement. So you can see that as I scroll through here, the peaks, some of them just kind of disappear and then they return again. There's a measurement where this peak right here is hardly visible. But if I scroll through, it'll show up in some of the other measurements. Now we have something in MEscope called a quick fit. So with nice clean data like this, and once you're used to using the curve fitters in MEscope, and we're going to go through them all and I'll explain them to you. Quick fit is the way you want to go. You don't want to waste a lot of your time curve fitting data unless it's particularly difficult, and I'll show you how we can divide and conquer using these curve fitters, because curve fitting is really just a means to an end. I can have a curve fit function, you'll see in a minute, that lays right on my data, but my modal parameters may not be good estimates. So we need to go ahead and look at them in animation, maybe compare one curve fit set of data with another. We can do that in MEscope so that we are assured, as best we can be, that we are getting some accurate experimental data from the structure. Now I still have the cursor on here. Let me turn that off. So I'm going to click up here because I don't need a cursor, although we'll see that the band cursor is very useful, not the line cursor, but the band cursor for kind of steering the curve fitting in the direction that I want it to go. Over here on the right are some panels and an empty spreadsheet. This is where the results of curve fitting, well, the commands that I use and the results are going to show up. So you can see I got three tabs up here, one called a mode indicator. Well, that must have something to do with this picture down here, which is empty right now. There's nothing in there. Frequency and damping. There are a number of ways to get the frequency and damping of each resonance or each mode. We'll go through some of them. And then finally, it says residues and save shapes. So what's a residue? Well, that's a mathematical term for the height of the peak. And I won't go into the mathematics behind that, but essentially the thing to remember is it's the height of the peak, or a better word, a mathematical term, is the strength of the peak in each of these FRFs, each of these measurements. Now, the other thing that's unique about an FRF is that we are dividing the acceleration response by the force that caused that response in the frequency domain. So regardless of what the spectrum of the force looks like, and when I hit a structure like the gym beam with a hammer, it's going to excite a lot of frequencies. I want to do that. And it's going to have a certain spectrum of the force input, which is measured with the hammer, with a load cell attached to it on the head. But when I get to this stage, I've divided the spectrum of the acceleration by the spectrum of the force. So it's basically removed the frequency content of the force, and the FRFs simply have at each frequency, the response of the structure due to the force at each frequency. So that's why we use FRFs, because when I see a peak in these measurements, that peak is due to the resonance. It's not due to a peak in the force. For instance, in an operating or in a running machine, we're going to have peaks due to the RPM of the machine and multiples of the RPM. Those are called orders. They're going to force the machine to behave at those frequencies as a force response. And a resonance may or may not be involved. So with a running machine, we can measure a cross spectrum. That's called an output-only measurement. And we just have to assume that we don't know anything about the force, but it's a flat excitation. And that's sometimes a good assumption, sometimes not. Anyway, back to what we're doing here, and that is curve fitting this data, FRFs, a set of FRFs to get the modal properties of the gym beam. Okay, I'm going to go ahead and use the quick fit. I can right click here and well, I don't see it in my pick menu. Oh, here it is right here. It's in a sub menu called quick fit. And so I'm just going to go ahead and execute this command, and bingo, it's done, and we've just curve fit this data that you're looking at. Now, the first thing that happened was a mode indicator was created. So this red line down here has got some very sharp peaks in it, even though the measurements up above may or may not have sharp peaks like this one here. The mode indicator processed all the data and came up with this indicator called a CMIF. So what does that stand for? Well, that's called a complex mode indicator function. If I go over here under the mode indicator tab, right there on the mode indicator is the CMIF. So that's the one that was used as a default, and that was computed for all the measurements. Then a peak picker went through that CMIF, and it found 10 peaks, and that's what's listed here on the tab. And so the Count Peaks button was automatically executed by Quick Fit. It found the 10 peaks, and that was needed in order to say, okay, I found 10 peaks in the indicator, there must be 10 resonances. Now there could be more. And that's when we get into what's called multiple reference or multi-ref curve fitting, where there's actually more than one mode represented by each resonance peak. We're not going to get there today. We're going to stay with the simple curve fitting, where we're simply looking at, we're assuming that each of those resonance peaks corresponds to a single mode of vibration. And you can see the mode indicator found two closely coupled modes here. Let me just zoom in here a little bit, and you can see that there are two resonance peaks that are fairly close together, and we don't even see the evidence of one mode. There's a measurement where we can't even see that resonance peak. So if I were simply counting the peaks in that measurement, I would have missed that mode. But the mode indicator does a good job of finding the peaks by looking at all the modes or all the measurements. Now this frequency and damping, what the Quick Fit uses is something called a global polynomial fitter. And we got a local, and then we got a multi-reference in here. But we don't have multi-reference data right now. This is single reference because our reference is 15Z. The reference is always behind the colon, and the roving DOF is always in front of the colon. So in this case, the multi-reference, I could use the multi-reference curve fitter, but it would treat it like single reference data. Okay, that was the frequency and damping method. So curve fitting in MEscope is 3 steps. First a mode indicator, then the frequency and damping, then the residues. And we have a couple of different methods here. One called a peak method, a polynomial. That was the one that was used. And then we got some other methods in here that we'll come back and use in a minute. But the result of the curve fitting was this data down here in this spreadsheet. So I have frequency, I have damping, damping in hertz. Remember I told you that the damping of each mode is the width of the resonance peak. It's a measure of the width. That's called the half power point, or the 3 dB point, or the modal decay constant. Number of different terms to describe damping in hertz. But if it's going to be the width of one of these peaks, then the units have to be in hertz, because that's the x-axis of my data. It's frequency domain or in hertz. Now the more common term for damping is percent, and that is a short version of what's called percent of critical damping. Now the percent of critical damping means that, well, mathematically it's the damping in hertz divided by the frequency in hertz. Not quite, but there's a difference between this frequency here, which we call the damped natural frequency, and another value of frequency where we take the square of these two numbers, sum them together, take the square root of that. That's called the undamped natural frequency. Now we don't print that out here, but it's just the sum of the squares, square root of the sum of the squares of these two numbers. The damping in percent is in fact the undamped natural frequency, or the damping in hertz divided by the undamped natural frequency. And you can see these are all very lightly damped. The values are 1%. Here's some heavily damped. The 461 hertz is 2%. That's that most heavily damped. In a percent, oh no, here's 2.9 up here, the 224 hertz mode. Now these are all selected. You can see that if I unselect them, I get some vertical lines at each of the natural frequencies down here on the mode indicator. Let me zoom in again here around these two modes, and So those are the 461, you can see it turns red, and the 492, it turns red. And those modes are coupled, they're fairly close together. One has damping of 10 hertz, the other has damping of 4.5. So quite a difference in two modes that are fairly close in frequency. Why would that be? Well, we have to go back and look at the mode shapes of those two modes and how those two modes are being affected by the damping mechanism. Now, when we talk about damping mechanisms, there could be many mechanisms that are causing these two modes to be damped differently. Let me just arrange things so we can look at the mode shapes again. Well, I'm going to draw this over so we get a bigger picture here of the structure. So we're talking about these two modes here at 460 and at 492. The difference between them is going to, and damping is going to be a function of their mode shapes. Well, how would this structure be damped? A couple of things that I could think of right away, and one is the surrounding air. That's a viscous fluid that's absorbing energy from the structure, and the other is the foam rubber that it was sitting on, which is also going to absorb some of the energy out of the structure at those two frequencies. So the mode shapes of those two modes are going to tell us when we see them what the difference is between, the damping being more than twice as much between the 460 and the 492. 461 hertz is being damped out much more heavily than the 492. We'll come back to that. Well, I've got some results here. Actually, I can go ahead and animate them right here from this spreadsheet. So I can animate while I'm curve fitting, and let's go ahead and do that. Let me see if I can find the right command to do that. Animate shapes. So let's see what happens here. Okay, there's the 461. You can see I can only animate one at a time. It's selected the 461, and that's what I'm looking at on the model. So you can see there's a lot of bending of the bottom plate there, which is probably being influenced pretty heavily then by, or it's absorbing the damping of the foam rubber. And so that's why this mode is very heavily damped. Let's click on the 492. 492 is a torsional mode, and that one is not being as affected as much by the foam rubber. Now, I'm just guessing that the foam rubber is causing the extra damping here between the twice as much damping. Percent-wise, well, even percentage-wise, quite a bit. But I'm looking more at the damping in hertz, the half power point, or the damping decay. That's the true decay of a damping envelope if I were to simply look at the decay of one mode versus the other. Okay, so we're done with this. The last step is to save our data into a shape table. So let me go ahead and do that. And so I'm going to come over here, and it says Save Shapes. Now, what's it going to save? I've got one value of frequency and damping because we used a global fitter as opposed to a local fitter. That was back here. You can see the global fitter was the defaulted choice. I could have used a local polynomial fitter. I would use that in cases where I had some mass loading due to the accelerometer, or I had some what's called non-stationary behavior of the structure while I was collecting data. And if I had fluids moving in and out of the structure, or the stiffness was somehow changing due to the environment as I took data, then the resonance peaks are going to move around from one measurement to the next. Let's put those back up here while we're talking about that. And if I overlay the resonance peaks and they don't line up, then I may want to use a local fitter, which will fit each of the measurements individually and come up with a local estimate of frequency and damping. The curve fitting may work a little better. In this case, we used a global fitter, and the global fitter assumes that the frequency, the peak is at the same frequency in all the measurements, and it just goes through and curve fits all of them. The other thing that you're looking at here when we look at the curve fit is this red line, which is a fit function. Now that red line is an indication that the fit, the parameters did a good job of matching between the experimental data and the analytical fit function, which had the unknown frequency and damping and residue in it. Remember, the residue is the peak value. So let me just change this. You can see if you watch over here in the spreadsheet, the residues will change, the frequency and damping will not change as I scroll to a different measurement, because we used a global fitter, and that just came up with one estimate from all 99 measurements for frequency and damping. However, the peaks change from measurement to measurement, so the residues are going to be different. And they're complex, so they have a magnitude and a phase. As I just change this to another, well, you can almost watch as I'm scrolling here that the residues are changing, magnitude and phase. So each of those, when we do the residue fit, each measurement had to be curve fit individually. We couldn't do a global fit of the measurements to get their residues. So when we save this data now, we go back over here to this tab that says save the shapes. What we're really saving as a shape are the residues for each of the individual measurements. Now remember that the measurements were, here we are animating, they were taken at each of the points in the X, Y, and Z direction, so the residues that I save are going to give me a mode shape in each of the 99 directions also, 99 points and directions, what we call DOF. And of course we're still animating here right off of my residue data, animating all of the residues onto the model. So when we save shapes, really nothing changes other than they get saved into a different spreadsheet that we call a shape table. So I'm going to go ahead and do that, save shapes. And I've already got a couple of shape tables, the SHP meaning shape table, or an indicator of the shape table. One called imaginary peaks. Well, we were animating imaginary peaks, so I've got one that's, I could have just done a save shape of the ODS and save the imaginary peaks, but let's save these curve fit results into something called mode shapes. So I'm going to replace what's already in there with the result of the curve fit. And oh, well, I only got one, see, because I had that one selected. So that's not what I wanted. I wanted to save all of the 10 modes that I found. In MEscope, if I select the mode, then only the selected item, whatever it is, in this case the shape, was, or the mode was saved. So I'm going to undo that, and now the rule is if nothing is selected, then everything gets saved. So let's go ahead and do that again and replace, and now I've got all 10 modes in here, and over on the right are the what we call the DOFs, or the mode shapes themselves. So now I can, let me close out the curve fitting here, and let's arrange things. So now I've got my FRS up here that we were animating the ODSs from. Down below here I've got the mode shapes that I just saved. I'm going to start the animation again, but this time I'm going to do a, well, let's just start the animation from there. Okay, so that, now I'm animating mode shapes from my shape table. So we're seeing the same results that we looked at when we animated during curve fitting. We're just looking at the residues that have been saved for each of the modes in the shape table. You can see that we got 10 very nice looking modes. The lowest frequency here is the one we saw as an ODS when we were moving the cursor through the FRS themselves. We're looking at a nice clean mode shape. And then bending, what I would call in-phase bending, where the top and bottom, I'm looking at first bending of both top and bottom. There's out-of-phase torsion. There's out-of-phase bending. So we can give these names, but pretty soon we run out of names. So the best thing is just to say this is the, instead of the in-phase torsion, this is the 492 hertz mode. Now the other thing I can do is compare the ODSs that we were looking at to begin with the curve fit results to see how well they match up. This is another way to verify that curve fitting is doing its job. So if I go to compare shapes now, let me turn the point labels off here so they'll animate a little better. Now what I've got is on the left, I've got mode shapes. You can see my sources of mode shapes. On the right, I've got FRS. So I'm animating just the ODS by moving the cursor through the data. And on the bottom here, I'm still animating mode shape number 1. Now you can see the shapes don't match up too well. This measure here is also turned on. It's called the modal assurance criterion. Now that's a metric that's comparing the mode shape down here in the shape table with the ODS up here that I'm displaying by moving the cursor. Now when that metric is very low, when that MAC value is very low, that says these shapes are just not the same, and obviously you can see that. I've got a torsion mode here, and I've got something, a low frequency ODS here. So the MAC is telling me, so I can scroll this along until the MAC, bingo, there's a MAC almost 1. And you can see now the shapes match up. So the ODS is very similar to the mode shape for that particular mode. Now if I want to do this automatically, I'm going to go here to compare shapes, and you can see I've got a command turned on here called maximum MAC. And let me just turn that off for a minute. So now as I click along here, you can see that the MAC value is very low because the cursor is not moving here. And same thing, if I move the cursor up here in the data block, nothing is happening in the shape table. MAC, in other words, matching up the shapes. So now let me turn this on, and as I drag this along, you see what it did? It went through the shape table and said, here is the mode shape that matches up the best with the ODS that you're displaying at 635 hertz. And I can use this both ways. So if I go over here, as soon as I let go of it, there is the match of the ODS with the mode shape. Now if I go here to, now let me click down here on 461. And there is the best match of an ODS with the mode shape. And this is showing me that the curve fitter actually pulled out a nice clean mode shape on the left, but the ODS that I'm displaying is only 80%. That's the best match that it could find in the data. And remember, we were looking at the imaginary part, so let's look at the imaginary peaks up here in the FRF data and see if we get a little bit better match. So I'm gonna click over here first, and now I'm going to switch over and display the imaginary. Okay, now I've got 98%, and you can see that other than a phase difference, that ODS and that mode shape are quite accurate. Let me click on the other mode here at 492. Remember, these were fairly closely coupled, but now that we're simply looking at the imaginary part of the data, there's 100% match. So curve fitting and the ODS itself matched up pretty well. Let's just go look at some of these other imaginary peaks. Well, you can see that they are matching up very well, ODS matching up with the curve fit result. Now this is another thing to look for in your data when you have lightly damped data like this. And the worst case that we've had here is the 461 and the 492, but that's still a pretty good match, 98% match between the two. So when I have a lightly damped structure, this is telling me curve fitting has done a good job. I've got maybe a more accurate estimate of frequency and damping. Of course, the ODS doesn't give us any damping. It's just giving us the residue or the peak values of the data that I'm looking at. See, if I go back here to looking at, let's say, display magnitude, now I'm looking at magnitude and phase, and that's not a very good match. So if I'm going on imaginary, then I get the right peak. If I go to real, let's just go over here to real for a minute, that's not a very good match either. There's the real part of the mode shape, well, the mode shape on the left, which is complex, the real part of my ODS data on the right, and that's not a very good match. 79% is too low. That's just telling me that doesn't match up very well. There's, again, the best matching up the real part. So real part would be what we look for if we're got velocity data, because that would be single peaks. But you can see as I click along here in my mode shapes, there is nothing matching up very well if I just look at the real part. Let's go back to the magnitude again. We'll just go over that again. Magnitude. So this is now showing me a match of the magnitude and phase of the ODS versus the mode shape magnitude and phase. And there's a very good match. Very good match. Again, this is the worst case here with the closely coupled modes. Not a very good match, but the 492 is fine. And okay, well, I'm spending a lot of time here going through this simple case. Let's go back and I'm going to stop the animation and we're going to try some of the other curve fitters. Because one of the advantages you have with MEscope is that we have a number of different curve fitters in here. And what we can do is try different ones. And as I said, I always use a quick fit first to see what results that will give. And then, let's just say this is more difficult data. The next thing I would do is turn on the band cursor. Well, let's go clear out all these results first. So I'm going to go back here, and I have a command up here in my toolbar that says curve fit, delete all fit data. So this data is part of the data block, but I've got those results saved in a shape table now, the curve fit results. But now I can go through and use this quick fit, and if I've got some, I don't know, electrical noise, 60 cycle, 50 cycle, whatever it is, I don't want to curve fit that. That's not going to give me a resonance. But here I can go through very quickly with a curve fit, and I've got a button up here on my toolbar that says curve fit, quick fit. So it's going to go ahead and do that, and you can see that I got a very good match there in that band of those two. You can hardly see the fit function, the difference between the fit function and the data. And I got those two modes very cleanly. So let's go over here and let's just fit 3 modes here, because I know there's 2 closely coupled plus another one in there. I'm going to do another quick fit. Bingo. And again, it's using the mode indicator, the CMIF. It's using the global polynomial, and it's using the polynomial to get the residues. Okay, here's a mode sitting right here. Kind of a lone wolf there, not very well. But I can just go ahead and quick fit him there. He's not even showing up in that measurement, but we don't care. We're using a global fitter. And let's see how well that did. Well, when there's a peak in the data, it did a good job. And when there's no peak, there's nothing. And you can see the residue on that one is very small, 7 magnitude and a minus phase there. So that was not very good in terms of that particular measurement. But we don't care. We're using a global quick fit, and we're going to go through. Let me get this last guy over here. Now, the other thing to notice is that this data was actually taken beyond 2 kilohertz. It was actually taken to 3 kilohertz. And then we're only showing you 2 kilohertz here, and we threw away the rest of the data to illustrate a point that curve fitting always has to compensate for the effects of out-of-band modes. And you can see in this measurement, this is called a residual effect of some higher frequency resonances that were excited when we impacted with the hammer. Maybe we had no way to control that. And those modes are going to get excited. Those resonances are going to get excited. See, there it is again. The tail of a higher frequency mode, 1 or more, I don't know how many are out there. The curve fitter has to compensate for those. And how does that happen? Well, if we go back here, the polynomial fitters use extra numerator polynomial terms. I'm not going to go into all the mathematics, but this type of a fitter is using extra terms in the numerator to compensate for the effects of the out-of-band modes. So whatever curve fitter you're using, it doesn't matter. You better have some way to compensate for the out-of-band modes, because you can always have them in your measurements unless you can control the excitation so that those higher frequencies are not excited. But even at the lower frequencies, when I'm curve fitting like this, just a few at a time, I have to compensate for the effects of the modes outside the band. So that's where this fitter is very good at doing that, and I can use the quick fit in small bands. And there again, if I scroll through the data, I can see the red line is almost indistinguishable from my measurements, my measurement data. And that's what you want to see. Again, the red line is not sufficient. It's only necessary to getting a good curve fit. The real proof of the pudding, so to speak, is if my mode shapes are good and they compare with mode shapes I got from a different method. Now I can go back once I have all the modal data. I'm going to turn that band cursor off, because that is going to limit me to operating just in a band of data. Now I have another command up here called fit function synthesis. So now that I have all these measurements, and again I have the number 10 selected here, so I have the 10 modes all identified. I want to unselect, and then I want to synthesize a fit function to see how well it matches up with my experimental data. There it is. You can see that it's pretty good. There's a little bit of a disparity between the fit function there and the measurement data, but pretty good match, especially of the higher peaks, because that's where those modes are very well represented. But you can see I can go through even some very ugly data and kind of divide and conquer. Let's save these shapes, and we'll create a new file, and we'll call it, I don't know, quick fit banded. So I got some data there. Now let's go back and use one of these other fitters. I'm going to clear out all the data. Let me go back here and find the command that says you want to clear all your, it says clear all fit functions. We want to do more than that. We want to clear everything. All your data will be deleted. Do you want to continue? Yes. So now we got a clean slate again. Just the measurements on the top, no indicator. Now I'm going to go over here. Let's just put up an indicator. Well, we don't need to. Let's go to the stability diagram. Now this is a curve fitter that's going to assume that we don't know how many modes are in there. Remember, with a quick fit, it goes to the mode indicator and counts the number of resonance peaks. Then it tells the frequency and the damping fitter, how many modes to do the quick fit on, and that's how we get the estimates in the mode shape table, or over here in the curve fitting spreadsheet. Now I'm going to use something called a AF poly, and this is a different method. I've got 3 different methods in here: complex exponential and something called a Z polynomial, and then the multi-reference versions. This is part of our multi-reference curve fitting, where we can use a stability diagram to curve fit, where we let the diagram tell us how many modes are in the data, not necessarily the indicator function. So this is good for more closely coupled things. For OMA data, we're not going to get to that today. We've already spent our hour. So let me just go through here and go ahead and say, do the stability, and then let's just take a look at what it did here. Okay, it's a little hard to see. Let me change the colors, and I'm going to go and do that in the options box. These colors are being used here. These contour colors, the first 2 are being used. So let me just make this one a blue contour color, and now you can see that it changed. And what I got in my stability diagram now is an estimate of frequency and damping. And the frequency, if I zoom in here, let's just zoom real tight, and you can see that what it did, and over here, it went in and it said, curve fit this data with, well, down here, 1 mode, 2 modes, 3 modes, 4 modes, all the way up to 50 modes. So the curve fitter ran 50 times with a different number of modes in it. And then all the answers are plotted out here. The width of the little bar is the damping estimate, and the little dot in the middle is the frequency estimate. So this curve fitter went through, and then they were all laid on the diagram here, so I can see where the curve fitter got some consistent results. So let me zoom out here for a minute, and oh wow, we lost some of them. I'm going to have to do that over again. Let's go back here and do that again. Okay, so there they are. The display got rid of them, but there they are. They're all up there. So what we're looking for is a consistent value of frequency and a consistent value of damping. I can go in and select any one I want off of this diagram, or I can just say save groups. And what that means is I'm going to save an average value of frequency and damping for each of those vertical lines there, where the frequency is the dot in the middle, the damping is the width of the little horizontal line. So you can see we got 15 modes, and we got some of the rigid body modes down here at the low frequency. They were also curve fit. So the first 164 is what we got from the quick fit, and then we got 3 extra of the rigid body modes. But how well did we do here? Well, let's go ahead and do the final step, residues. Let's just look at the residues now and see, now that we got them, there is a fit function. Is it good? Well, maybe not as good as I expected it to be, but again, we got a little problem with this mode right here. I may want to go in and try some different things. That one seems to be not getting a good estimate of the residue, the peak. But let's just go see what the shape looks like. I'm going to go ahead and save these, and let's create a new file, and we'll call them the AF poly modes. Okay. All right, well, we can go ahead and start the animation. We're used up our hour. Too much talking here today. Let's put this one up here. We got the mode shapes down here. Let's get the, well, let's just go ahead and see what we have here. So we've got mode shapes from our quick fit. We got some AF poly up here. Let's just start the animation and compare and see how well they compare. Okay, so there they are. First one, and oh, we're still animating the FRF, so I want to go animate the AF poly modes. There we go, AF poly versus quick fit. 99%. You can see that it ignored the first 3 and went and compared the 164. There is the result. And you can see that mode for mode, the stability, even though we averaged together a lot of values to get those mode shapes and the frequency and damping, we got a very good match. And so the ones up here in the global probably don't have a good match at all. We can look at them. There's one of them that doesn't match very well with any of the quick fit, but it's a rough looking version of the rigid body modes. So that's what the curve fitter found. But then when we go to the first flexible mode, we got a very good match between the 2 curve fitters. Anyway, there's more things to show. We got more curve fitters in here. We could have compared some more, but our time is up, and we're going to say goodbye. Brian, do we have any questions? We forgot to bring that up at the beginning of the webinar. If there were questions that you could...
No, we don't.
All right, well then we'll say goodbye, and next month we'll have another webinar, and thanks for coming.